Today we're going to look at a couple of special cases for integration and particularly before that actually a couple of uh, types of integrals that might show up on the AP test. And especially some ones that are going to be really important when you get to some more complicated techniques in Calc 2. They're going to expand on some of these a little bit, but these are ones that you really want to know already going into Calc 2. And then occasionally it'll show up in the multiple choice. So the first one we're looking at here is an integral of 2 over x plus 5 dx. And so kind of like we did with some of the u sub integrals in the previous lecture, we're just going to u sub out that denominator. So we can see that for the first one here, if we let u equal x plus 5, du then is just 1 dx, or just dx. So this makes the substitution really quite easy. This ends up being 2 du over u. Right? And the integral of 2 over u are just going to end up being 2 times the natural log of the absolute value of u plus your constant. And so we've got 2 natural log absolute value x plus 5 plus a constant. You're going to want to get to the point where you can just do that one straight away in your head without actually having to write out the u substitution. So if we look at this next one, we can see that this is going to be u equals x minus 7, where du is again just dx. So this becomes an integral of 4 du over u. So we'll have natural log, or 4 natural log absolute value of u plus our constant, where u is just x minus 7. So I don't really need to write out that intermediary step where I just have the u inside the absolute value of u. Don't feel it. And for the last one here, we've just got slight little change to it. This time u is going to be 2 minus x, but du will be negative 1 dx, or a negative dx. So this time we're going to have to throw a negative inside and negative outside. So this will become the opposite of the integral of 3 du over u. And that'll just become, and again, that negative could be inside or outside. This will be negative 3 natural log absolute value of u, and u is 2 minus x plus a constant. So this particular type of integral, where we've just got a simple binomial in the denominator, shows up pretty often, especially in Calc 2, but also sometimes on the AP test, both in the multiple choice and sometimes the differential equation FRQ questions. And differential equation is going to be our next unit, so this is going to be useful to us there as well. Probably get used to problems like that. In this case, we're looking at an integral of x squared minus 5x minus 3 over x plus 2 dx. And so this is similar, except the numerator is no longer just a constant. And so the rule that we're going to want to kind of come up with here that's going to be carried over into Calc 2 as well is that anytime you're left with a rational function, this is definitely a rational function, it's a polynomial divided by a polynomial, in which you don't see another quick, easy, good way to do it, like a real basic u substitution that'll work out nicely for it. And if the degree of the numerator is either greater than or equal to the degree of the denominator, you're going to want to divide this. So we're going to divide x squared minus 5x minus 3 by x plus 2. So we could do long division, but I'm not a big fan of long division. I'd rather just do synthetic division. So I'm going to put a negative 2 up in the box here because negative 2 is what makes x plus 2 equals 0. And I'll list my coefficients going across: 1x squared, negative 5x, and negative 3. And again, the way synthetic division works is you take the first number, drop it below the line. You take any number below the line and multiply it by what's up in the box. So I'm going to do 1 times negative 2. That'll give me a negative 2, and that'll go up into the next column above the line. And once you have 2 numbers above the line, you just add them together. So -5 and -2 is going to give me -7. And now that I've got a number below, I'll just multiply it by what's in the box. So -7 times -2 gives me 14. And I'll just add those together. -3 and 14 gives me 11. And so the first value there is an x, is a 1x. And we know it's an x, and not an x squared, because we've divided x squared by x, right? So we're dropping by a degree of 1 from where we start. So it's 1x minus 7, and then plus our remainder of 11 divided by our original denominator, x plus 2. And so now we can see what the use of that was, especially thinking about what we did on the previous page. We can now just integrate the x squared over 2, and the -7 is -7x. And of course, if I wanted to, I could add a constant. But I'm going to just hold off on that for right now. This becomes just an integral of 11 over x plus 2 dx. So I'm going to get a second constant when I integrate this, and when I put them together, I'm going to do that with just one constant again. So we'll do that same u substitution from the previous page. So we're going to let u equal x plus 2, where du is just dx. Turning this into x squared over 2 minus 7x plus 11 du over u inside of our integral. And we'll then just end up with x squared over 2 minus 7x plus 11 natural log absolute value of u. And instead of u, I'm going to write x plus 2. And then I'll throw our constant down there at the end. And so the goal will be to get to the point where you can do these little integrals that require the u sub by just doing that u sub in your cat too to write that extra step. And hopefully you can just go straight from right here to the answer pretty soon. So again, here we're looking at a rational function, a polynomial divided by another polynomial, in which the degree of the numerator is greater than or equal to the degree of the denominator. So we'll just do some division. And again, it can be long division or synthetic division. We'll do synthetic division since it's an x minus 2. All right. And we'll put our coefficients 1x to the 4th. We have 0x cubed. Don't forget the 0 since there's no x cubed term. We have minus 3x squared. We have a positive 2x and a negative. And again, the synthetic division will drop the 1 down, multiply it by the 2, and it's in the box. We'll add the 0 and the 2 to get 2, multiply that by what's in the box to give us 4, add the negative 3 and the 4 to give us 1. Again, the 1 times the 2 up in the box gives us 2. We'll add the 2 and the 2 together to get 4, multiplied by the 4, the 4 by the 2 that's up in the box to give us 8, and add the negative 3 and the 8 to give us 5. So this divides out to become an integral of x cubed. We're dropping down by a degree of 1. We started at x to the 4, so it'll drop to x cubed. X cubed plus 2x squared, because we have a 2 as the second thing in our answer there. So 2x squared. Then we have another 1, so that'll be a plus x. Then we have the 4, so that'll be a plus 4. And then the 5 will be plus 5 over x minus 2 dx. And I'm not going to write out the whole u sub for the x minus 2 this time. We're just going to kind of think about it. Right, I'm not going to write out all the integrals. But if u is x minus 2, then du is just dx. Right, and so all these other ones just get integrated as usual. And then this one here is going to look like 5 du over u. And when we integrate 5 du over u, we're going to get 5 natural log absolute value. So we end up with x to the 4th over 4, when we integrate the x cubed, plus a 2/3 x cubed, plus an x squared over 2, plus a 4x. And then, as we said here, we'll have plus 5 natural log absolute value x minus 2, plus our constant. We'll do a couple more here. So this one is very similar to what we did at the beginning. We got the integral of 2 over 3x plus 1. But this time, when we try to do the u sub, u is going to be 3x plus 1, which means that du is going to need to be 3 dx. And so we don't have a 3 dx, we have a 2 dx. So what we'll do is we'll take that 2 out into the front to begin with. And we'll have dx over 3x plus 1. Right? We can pull that constant out of the integral if we want. And we're going to need to then multiply by 3 inside, which means we'll divide by 3 on the outside. So we end up with 2/3 of the integral of du over u. And so we'll now just integrate that. That'll give us 2/3 natural log absolute value of u plus our constant. And a similar process down here. We're going to let u equal 3 minus 2x, so that du is negative 2 dx. Now we don't have a negative 2, we've got a 4. So if we pull out part of that, if we pull 2 of it out of there, right, we'll have a 2 on the outside, and we'll have an integral of 2 dx on the inside, with the 3 minus 2x in the denominator. And we'll need to throw a negative sign inside of it, which means we'll need to throw a negative sign on the outside of it, turning this into negative 2 times the integral of du over u. And we've done enough of these, I think, to see that this is now just negative 2 natural log absolute value of u plus our constant. So we're going to finish today up with a couple of quick special cases that on rare occasions pop up on the multiple choice of DAT test. It doesn't happen very often, but it's good to see the technique, and you're going to use these a lot in Calc 2 anyway. So we want to integrate 1 over a squared plus x squared dx. And if we look at that, it looks awfully similar to how we would integrate something to get inverse tangent. And that's exactly what's going to end up happening. But we got to do a little bit of work, because for inverse tangent, we can't have some number here other than 1. That a squared would have to be a 1. So the only way to make the a squared a 1 is to divide it by a squared, right? Which means I'm going to have to divide the x squared by a squared as well. And to even that out, I've also got to divide the 1 that's up in the numerator by a squared. So we're first going to complicate this integral just a little bit here, so that we end up with a 1 down there in the first part of our denominator. So as I do this, the 1 over a squared that's up here is just a constant, right? Because a is going to represent a constant value. So I can pull that constant out as a 1 over a squared in the front of this whole integral. And I'm going to be left with now just a 1 over a 1 plus x squared over a squared. Right? This x squared over a squared that I've got right here, I'm actually going to rewrite that as the quantity x over a, all being squared. And the reason I'm going to do that is so that I can now substitute out x over a as u, because then I'm going to have inside my integrand just 1 over 1 plus u squared, which is perfectly going to integrate into inverse tangent of u. But before I can just make all of that happen, I've got to see what du is. Well, the derivative of x over a constant is just 1 over that constant. So 1 over a dx. Well, unfortunately, I don't have 1 over a there. I could have if I hadn't pulled out the 1 over a squared, but I don't. So let's just multiply by 1 over a. But if I multiply by 1 over a on the inside, I've then got to multiply by a on the outside. So this is going to come down here, and on the outside now I'm going to have a constant of a over a squared. A over a squared is just 1 over a. And then on the inside, I've now got an integral of, well, let's see, 1 over a dx is du. So I've just got du over 1 plus x over a squared. Well, x over a is just u. So 1 plus u squared. And now this will very nicely integrate out to 1 over a times the inverse tangent of u plus a constant. And of course, we'll convert it all the way back. U is x over a, so this is 1 over a inverse tangent of x over a plus some constant. And so that's going to be our integral of 1 over a squared plus x squared. Now you can memorize that rule if you want to. I think it's a good one to just know. But if you had a problem where you had something in there for the a squared, for example, let's say we had a 9 in there, we could either just use the formula, or we could go through that same process. We'd divide everything inside of it by 9, and then simplify it down and do that same sort of u substitution. But since we can recognize that this is of the form, right, 1 over a squared plus x squared, where a must then equal 3, we should be able to go straight to our answer using our formula, right? Our formula said it's 1 over a times the inverse tangent of x over a plus our constant. So knowing the formula makes that problem just a whole lot easier. But again, it's not necessary for you to memorize the formula. You can always go through and do that yourself. So we're going to do another one here, and you could probably, if you take a second to think about it, probably guess that this one's going to come out something involving an inverse sine. And you'd be right. So we're going to do the same kind of thing, because instead of an a squared in there, we're going to need that to be a 1. So the first thing we'll do is we'll go in here and we will rewrite this. And I'm going to do the denominator first. So I'm dividing that a squared by a squared. And I'm dividing that x squared by a squared. So that this a squared over a squared is just 1. But I'm not really dividing by a squared, because I'm dividing by an a squared that's inside of a square root. So really, all I'm actually dividing by is just an a. So in the numerator, I'm just going to divide by a. And if we kind of follow that same trajectory as the last problem, this ends up being an integral of 1 over a over the square root of 1 minus, then again, x squared over a squared is just x over a squared. And we're going to make the exact same u substitution. We're going to let u equal x over a, so that du is just 1 over a dx, which we can see is sitting right here in the numerator of our integrand. So this will just end up becoming an integral of du over the square root of 1 minus x over a, or u, squared. And now this is just the exact same thing as the derivative of inverse sine. Our integrand is the derivative of inverse sine, which means the antiderivative should just be the inverse sine. And it's the inverse sine of u plus a constant, or the inverse sine of, what was u? It was x over a plus a constant. And so we'll real quickly just do one problem where we just follow that formula. Right here we've got the form 1 over the square root of a squared minus x squared. where a is equal to 4. So our integral should then just become the inverse sine of x over a, x over 4, plus our constant. And that's going to be it for our special cases and other kind of common integrals that pop up using those natural logs like we did at the beginning. And that just leaves us with one more topic for the remainder of this unit, which we'll talk about next time, the mean value theorem for integrals.